Teste 1, 2, 3. Testing 1. Tem.
Portuñol? Oh, yeah, it's much better than Portuñol. Wow. If I say propina, this goes very wrong. I mean. If there are questions, also online, I can answer. I don't know. Which system do you use? MS Teams or Zoom?
No, it's YouTube.
YouTube, okay.
Will the video stay on YouTube?
I think so. It's out.
La que me faltaba. Sure, sure.
But I don't have a microphone. Yeah, I think it's easier.
Yes. Well, if not,
I will need to put a microphone.
okay.
No, you can take this.
Take this, the big one.
Tem microfone de volta, tá? So I think I just say that you are from Wageningen University.
That's good. Very good.
And then if you want to add more,
Very good.
feel free.
Excellent.
So, hello everyone, good afternoon. So today we're going to have two seminars, one with Jordi and one with Oscar. And they did an experiment in the Amazon a cloud roots, and they're going to present the overall results from this campaign and the motivation behind it. And I hope you enjoy.
For the to see that these cloud roots will not really provide all the logistics and quite a lot of the science here behind. So I would appreciate very much. I'm going to give a presentation of half an hour. Mainly is about everything about cloud roots, and then Oscar will go a bit more in detail on one of the instruments that we use in cloud roots. It's called scintillometer, and then we use during Café Brazil. And I would like also, because we have been discussing this morning with quite a lot, that it will be very good because the collaboration with Luis has been very profitable, and also with Michael, that if we could really keep on this collaboration in the coming years. So the data and the modeling is very interesting. And this picture shows a bit what we try to represent. It's a situation that happens. We have a bit of a shallow cumulus, deep convection. You see the rain that happens. The picture is taken from the Atto Tower. And what we are very much interested is to have a bit of interaction between that sort of clouds and also how photosynthesis is taking. And by photosynthesis, I'm myself a physicist, I'm very much interested how the plant is regulating the water vapor entering in the atmosphere, what we call it evaporation. So we think that if the plant is stressed, will be less evaporation, and also the interchange between carbon dioxide and evaporation. So we are taking biology as an important part of the ecosystem that is in the Amazonia. And this is what I call it the challenge, because what do the models do? And first I'm going to present models that is called CIMEP6, and CIMEP6 is 16 ensemble climate models that they have been used, and this is the first time that they put a plant physiology model to represent this exchange. And I'm going to present two pictures. One is the percentage of total cloud fraction, and this is the region of the Brazil with the Amazonia, and this is what we call it the net ecosystem exchange. This is the exchange that the plants are really just uptaking carbon dioxide. If it's negative, is that the plant is assimilating. If it's positive, is that the plant and soil are giving away carbon dioxide. And what they are comparing is the difference between present and pre-industrial conditions. And radiation is the same that pre-industrial conditions, and it's only the influence of the plants. So it means how much plants, if you have high carbon dioxide, a question to the audience. If you have high carbon dioxide, are the plants happy or not happy? You have a lot of carbon dioxide here. Imagine that you have, instead of 400 ppm, imagine that you have 700 ppm, like it's double. Are the plants happy to have a lot of carbon dioxide in the room? Yes. Yes. That's very good. And it's called fertilization of carbon dioxide. So this is due to that sort of change. Radiation is the same, and this is what the models give, and it's quite an important thing because it's the total cloud fraction, and it's a change of 2.7, but look to the changes of the naked ecosystem exchange. So I insist, this is only because the plants are feeling that it's a double of the CO2. And these are some sort of models, what they call it the sensitive models to the surface temperature. But if I move to this, remember the numbers of blues. If I move to the non-sensitive climate models, we have a completely different picture. So I don't know, here you can really see that it's a very small change, even an increase of clouds, and here you change also a change of the net ecosystem exchange. In Spanish we will say, yo solo sé que no sé nada, if I see that sort of climate models. I mean, it means that climate models, these are using a grid of 100 kilometers, are very bad, the key word here that I will use, are very uncertain. So this is what we would call it the top-down approach. So we try to get the climate, we change radiation, plan, and so on. But in cloud roots, we went to the bottom-up approach. So we thought, well, let's study in detail during 3 weeks what's going on with the plants at leaf level, at canopy level, and a bit also at large boundary layer and cloud scale. So what I'm going to give in the coming 25 minutes, it's a bit of the measurements that we did, starting what we did at leaf level. So I'm not going to say that this system is the one that we see in the Amazonia, and I'm going to summarize that normally we have air masses, very rich in water vapor, that they are coming from, in that case, the Atlantic Ocean, and they are entering, and we have shallow cumulus. But this also happens in the subtropics of Southeast, and this is also the Gulf of Mexico. And you have here again, these air masses, no clouds, they are entering shallow cumulus and sometimes deep convection. It happens also in the Netherlands. I don't know if you have been there, and this is the northwest, and no clouds here, all of a sudden, shallow cumulus and formation of deep convection. So, and also on the boreal forest. So this is something that happens as a part of the Earth system. With the idea, with the challenge that the Amazonia is tropic, this is subtropical, this is what we call it temperate, combination of forest and grassland, and this is what we call it the boreal. So part of the project is at one point trying to extend it not only to the Amazonia, but to other sites. And I can summarize it like this, with this sketch where we have the ocean a long way, and here it's an important thing that one of the things that we would like to do is that there is what we call it moisture recycling, that during the traveling of these air masses, and if this, we imagine that we have the Atto Tower here, there is 5 or 6 times that the water will be combined with the exchange with the canopy and finally will form clouds. And here also the importance of water, carbon, and what we have been discussing this morning, gas and aerosol. We have a list of the challenges that we still don't understand. One of them is 3D radiation. We are normally in the models having 1D radiation on top and so on, and this is a very big simplification. So the other thing is also how we combine turbulence and chemistry and canopy, and also one of the things that here I think you know much more than me is the transition between shallow to deep convection. With the idea that finally go back to the first slides to get better what's going on carbon and climate. So what was cloud roots? We had 3 weeks of a campaign and we have a lot of questions. The first one is how are photosynthesis and photolysis influenced by the disturbance of radiation? The second, it was about the atmospheric composition and also how it impacts turbulent transport, mixing, convection, weather variables. So here is more what we call it leaf level. This is what we call it canopy level. Also, how do these physical, chemical, and biological processes interact between local and regional? How these air masses that they are coming from the ocean that have been recycled with moisture are changing. And also the final idea is to understand this system of energy, water, and carbon, integrated over scales, to have good predictions at the present, to understand, but also in the future. So, first question, photosynthesis. And the first thing that we did, it was to measure radiation. And we had a lot of instruments measuring radiation, and I'm going to walk up this. So this is a typical day, 8th of August, 10 o'clock in the morning in Atto, 10 o'clock in the afternoon, and we have one measurement above the canopy on top, another in the middle tower profile, and this is the clear sky. So you see that in the morning, above the canopy, and a measurement that is inside of the canopy, remember that the canopy in the Amazonia is 36 meters, is the same. So you have the same measurement. All of a sudden, clouds start to show up, and here we see that radiation is higher because there is reflections of the clouds. So if you have a cloud here, you will have the direct radiation, but on top you will have the reflection. It's yeah, the finger is excellent. So you have the direct and reflected, and it seems that the canopy has certain holes, so the radiation, the canopy does not notice. But it changes during the night, during the afternoon, and then the solar zenith angle changes, and then there is a big change between the above canopy and inside. So what we get on radiation is totally different, and this is a very dynamic system, not only for biology, but also for chemistry. Photolysis depends on the radiation. So that was a result that still we need to work out. Second result, and has an impact also, and here I'm going to present, has an impact on, this is the, what we call it leaf photosynthesis. This is the amount of radiation that you reach, and you see that radiation gets some sort of saturation, but in the region where it's sensitive to clouds, any change of radiation will make that from this one to a big change will be that it's going to be a double of the photosynthesis. And a double of photosynthesis, it means that the plant is exchanging water vapor. And from a meteorologist like us, it's very interesting, that sort of thing. So again, that sort of trade-off between carbon and water and what is more optimal. And the plant is sweating like us, so he needs also to regulate the water vapor. So the second thing that we measure at leaf level is what we call it GS. I don't know if you are familiar. Is any biologist in the room here? Okay, perfect, because I am not a biologist, so if I say some stupid thing. We call it conductivity, and this you have to take it, it's like the mouth of the stomata. How is in Portuguese? Stomata? Ah, el estómato. La apertura y fechado de la stomata. Goes okay? Mejor que propina. And what is measuring is quite funny. This means that it's totally closed. This means that it's open. And we measure at different, we had some tree climbers. It's unbelievable how they are going climbing and down. But what we see mainly, it's a lot of scatter. But what we saw is that mainly we have, this is for instance the top shade, top sun, medium sun. So we were measuring in a lot of conditions. But the main result is around 12 o'clock, there is less photosynthesis. And it looks like the plant is like us. I'm coming from Spain. In summer, after lunch, siesta until 7 o'clock. So no photosynthesis. Photosynthesis in the early morning, we were saying that the plant was very open. As soon as there is some light, the plant was very open and eager to do photosynthesis. But around 12 o'clock, it was going down. So it means also, and I think that's also something that we would like to put in our models, that photosynthesis has a midday depression. The exchange of water is larger during the morning and less in the afternoon. So that was also a result that we get with this data. Then what we would like to put in the model is these effects of radiation, because the ones that I would mention, and here you see the change. This is a large Eddy simulation. Large Eddy simulation is a model that resolves very explicitly radiation, clouds, and so on. And I'm going to show one thing is this one-dimensional, three-dimensional, and you see that when we have three-dimensional with these effects, you see that the sensible heat flux is totally changed. So this is the sensible heat flux. You see a totally different spatial structure here. So it means that the heat that we are putting in the Amazonia with 1D or 3D is totally changed. And this has a huge impact on the cloud formation, because the heat is bringing up the thermals and then is transporting moisture, carbon dioxide, species, and so on. So in our models, it's very important to have that sort of 3D radiation. Second question, how is atmospheric composition? I need some water here. How is atmospheric composition? And here we go to a lot of detail. Again, this is a large Eddy simulation, and I'm showing 1,000 meters and 60 meters. And I'm showing moisture here. And this is the canopy top. And what we are trying to represent, the model represents with a grid of 3 by 3 by 3 meters. Remember that the first grid that I show is 100 kilometers. Here we are interested to get maximum detail. And this is what happened in the canopy, that it's sometimes the canopy has ejection motion, so moisture is put in, and some sort of moisture is going down. So the combination of turbulence plus this radiation that I mentioned at the very beginning, we want to enter in a lot of detail. And here also the chemistry can be very important, because this is where the chemistry is being cooked. Isoprints are really just their form, and they are forming particles. So the level of detail and the level that Atto has given us, it's going to be very important to have all the measurements in Atto on radiation, fluxes, mean, because here we can get a lot of detail. So just an idea, this is a large Eddy simulation with no canopy, and this is a large Eddy simulation with canopy. And I'm showing here the net ecosystem exchange, and I'm showing at 10 o'clock, 12, 13. So this is the flux of carbon dioxide. And you can see that as soon as you put canopy, you have a totally different picture of the flux. So these are very expensive runs, but the idea to have a multi-layer canopy model, especially from the Amazonia, is extremely important, also for the chemistry, okay? So again, This is the model that is trying to get all that sort of structures with eddies entering, eddies moving away, and something like this. And if you are in, I don't know if you have been in the atoll, when you are going down and so on, you notice that sort of very big differences and shafts of air masses moving in and out. So then we had also aircrafts that took almost quite a lot of this, and what I want to show here is we had a combination of soundings. Here I would like to say thank you to Luis and the team of Jorge Marton. We had a lot of soundings, and here what I'm representing is a specific humidity and the geometric height. And this sounding shows a relatively well-mixed layer, a cloud layer, and a free troposphere, and you have less specific humidity here. The same day, we were flying and had in carbon dioxide, and you see that the structure, no matter there is a scatter, if you are really doing an average, this is quite well mixed. This is quite with a cloud layer, and here you have also a different gradient. So again, is that the way that they are transported, chemical tracers like carbon dioxide or atmospheric composition, depends very much on the cloud structure that we have. So again, one of the take-home messages is that meteorology and atmospheric composition should be treated together. And not everybody. If you talk with chemists, they could care less about meteorology, and the meteorologists, they could care less about chemistry somehow. So we have a mission here to do here. Clear a bit the composition. It's very nice to see also the boundary layer. I don't know if you are used, this is the typical boundary layer, 1500 meters. So this is also unique data. And what we did also was to fly horizontal. Here is, these are plots that Oscar did. This is Atto, this is Campina. And the flight, they were flying at 200 meters. So what I'm presenting is the flight, the plane was flying almost 200 meters. And you see also, this is water vapor from 16 to 15.2. And this is CO2 from 2.5 and 2.18. But you see that there is quite, this is the river Watuma. But you see also that there is a lot of spatial variability. If you go higher up, the atmosphere is integrating very well. But at this low level of 200 meters, you see that there are significant changes of water vapor and carbon dioxide, though the correlation is quite low in the morning. And if I move to the afternoon, you see that the correlation is a bit high. So I think this is interesting data to show, and the level of detail. This was the last day of the campaign we managed, and it cost us quite a lot of money, but I think it was worth to really just do it. And I think it's very interesting to see how much is the spatial variability also. And I think it will be very nice to compare with the Atto Tower, Campina, and so on. Question 3, that it's important to have also Atto, and I think this is a picture a bit aside, but it's important to show that Atto has normally certain clouds, but we have also all sorts of clouds in Amazonia. And what I'm trying to say is that we are using principal component analysis to really, and I think we will do it for Café Brazil and for cloud routes, to analyze the size of clear sky regions and size of clouds and how the principal component depends on certain variation. So here the message is that we want to go to Atto Campina, but we want also to get a bit the bigger picture on how clouds are organized. And I think we are also working on that sort of self-organization of clouds to the large picture. And here we would like to add also what we call it moisture tracking. I mean, these are data that we got from ERA, and what we are trying to say is, where is the origin of the moisture? It's coming from very far away. Normally, majority of the moisture are coming from the Atlantic Ocean. We are calculating that there is a recycling of 30–40%, and I think this is Atto. So we would like to see that Atto is exchange of water locally produced, but at the same time also there is an advection of moisture that probably has an origin from the Atlantic Ocean, who has been moisture recycling. So we want to take Atto, but also to see how are the large scale forcings that they are coming. So just to finish, we are now trying to integrate observations and modeling, and here I will give two things. We are now preparing the conceptual runs and large eddy simulation, and then also at one point we would like to run the large eddy simulation embedded in a weather model. But for the first thing, we are analyzing the data, and these are information that was given by a master student from us, Vincent the Fighter. And what we are doing is we have all the data, we have classified following a paper from Henkes, we have classified all the data from shallow cumulus deep to shallow cumulus. In red is all the time shallow cumulus deep. And we are running a very simple model. It's a conceptual model, call it class. Quite good enough to give you an idea. The model takes 1 second to be run. So it's extremely cheap, but quite good enough, because you see that, for instance, it's a couple model. This is the sensible heat flux, and the evaporation does not go very well at the very beginning, but it's simulating quite evaporation. So it means that we have a relatively good forcings. This is in the canopy top. And then what we have to do is we have the radio soundings, and I will give you an idea, but this is at 6 o'clock, 9 o'clock, 12 o'clock, 15, 18, and we are running the model, and I'm going to give you a blow up here. So what we are doing is to combine the data from the ATO tower with the soundings. We have clustered the shallow cumulus with the shallow deep, and then we are running the model. Red is shallow cumulus, blue is shallow deep. And what is very nice is that the ATO tower coincides quite well with the radio soundings, so that's very good news. And once the model is totally well calibrated, we will move to this more three-dimensional model, large eddy simulation, and then we will move to probably other models somehow. But the whole idea is to use some sort of proof of the concept that the model is able to simulate surface fluxes and also the boundary layer. One of the things is that also we use the data from Campina, and I think we are using the method of Henkens here, and we are trying to distinguish between the shallow cumulus and shallow cumulus deep. Not so much, in a way, and these are the different stages that Alice Henkens defined, but one of the ideas is at one point to simulate also the cloud base and the cloud top and the different circumstances. And we are moving here in, and this is one of the last plots where we are simulating here the boundary layer that goes to 1200 meters. These are ready soundings, this is lifting condensation level. And what we are noticing is that there is not so much difference between the shallow and shallow deep convection. The boundary layer is growing, and I think here you see that the match with the soundings is quite good, but you see also that still there are things that can be improved on the model here, especially in the inversion. But here, with this model, you can do a lot of sensitivity analysis because it's very cheap to run, okay? So these are, what we do is integration of observations, run a conceptual model, run the large eddy simulation, but well define this, and in that respect, the data is very rich. The whole idea behind is that this is something that still is work in progress, is to put that sort of very detailed model in a very weather model. And that's a picture that I would like to finish. This is the Netherlands. I think this is Amsterdam. But the level of detail is very good. So we have here a weather model, and then we are embedding the weather model in a large eddy simulation. And this is evaporation. This is how much is evaporating. And any idea why there are these blue spots here? What are the effect of the, why are blue spots there in this area?
Clouds.
Clouds. So clouds are shading, less evaporation. So you go to a lot of detail on the map. And the other thing here, this is 1 o'clock in the afternoon or 2 o'clock. What can be here that there is some sort of, it's a very nice summer day in the Netherlands, happens not very often. But what happened here? What is the effect here that there is less evaporation compared to, and a very sharp front? It's a meteorological factor. What? I don't. The breeze. Yeah, the sea breeze. This is La Brisa Marina. It's entering humidity from here, and then the plants are really reacting. But the sea breeze is making, so you have all that sort of level of detail. That's it. These are the 4 challenges. And, sorry. This is a bit all the integration that we would like to get a bit that sort of level of detail of direct and diffuse, to have it in a more general context, to get the biology right, to get that sort of canopy effects, and also integrate these canopy effects with the transport of, in that case, moisture under shallow and deep convection, and finally try to integrate everything in a more large scale model. Thank you very much. I can take questions.
Let me know who is online if you want to ask some questions. I can pass along here.
It was in August. That was dry season. It was some 1 or 2 or 3 showers. So from the 10 days, we classify 3 or 4 like shallow deep, and the other are typical shallow cumulus. It was clouds every day. That's for sure. We are going to, well, I'm very much. We were, if you are interested, you can check. We were measuring monoxide, carbon monoxide and methane for this day, and we were seeing from the Atto towers some fires. So I think there were some peaks of CO, and I think for this day at least we have quite a lot of data, but there were some fires for sure.
And what aircraft? What?
It was a bit complicated. It was the campaign, the political campaign. So it's a guy called it's a NOAA. So the guy has to go. It's a private plane. Every time has to dismantle all the plane, put the instruments, and fly. And the first day, when he enters in Atto, the Brazilian Air Force cut it, so he got to return. So, and then the second day we managed to enter, and it's a private airplane. They have made some holes. Like this, yes. And he has all the equipment from NOAA. And I'm fascinating about the data because I think this is unique. The mind this, but I'm imagining this, and it's measuring water vapor, is measuring carbon dioxide, is measuring carbon monoxide, and is measuring methane. 4 compounds.
We have a question in the chat here. Umberto asks, GS drop in the afternoon. Did it mean radiation below the top canopy with less diffuse radiation?
Yeah, that's a good one. And I didn't have, so I think all the signs here, we have top sun, top shade, medium sun, medium size this. So it looks like, it means top sun and top this. It looks like all the measurements at different heights, all of them, they were dropping. So I think, indeed, diffuse radiation inside of the canopy is very important, so we need to have 3-dimensional models inside. But the general trend is that it was a total shutdown of the plant. It's very nice to correlate to vapor deficit. I think this is
he argues that it also has to do with the fact that it's a tall canopy, and it takes a lot of effort, hydraulic effort, for the trees to bring all that water up high. So when they start the day, they've been dehydrating in the night. But they cannot keep up with the loss during the day, and then
you have been in Atto, but this it's 6 o'clock and already the plan is open. So I think it's not stupid at all, and it says, well, this is the best time. I think also with the explanation of Oscar, So it's this water vapor is not, it's quite okay, but it's like us. I never go to the beach in the afternoon in Spain. I would get roasted and dehydrated. So I mean, and afterwards it's down. So it is a combination. It's quite complex. And the point is that we want to introduce this in the model. The point is, if you discuss with biologists, they say each tree is different, and I don't want to hear this. I want to have some sort of general tree that is behaving, and I'm not interested. It's like with chemistry. They tell you put 600 chemical reactions. I'm not interested in this. Give me 20 chemical reactions that they reproduce, and that's good enough. So from here, we have to have a model that is mechanistically reproducing this as a function of height. We are missing this hydraulic component, but it's enough to really just have this interaction with the meteorology.
Were there clouds in the afternoon?
Yes.
For shading the
Yes.
pictures?
Yes, so I think here what we are going to do, if I come back here, these are clouds in the afternoon. This is something that also, it's a quite important result. This is the clear sky. So cloud reflection is 20%, and it's very important for chemistry. It means that you have 20% extra energy here that is normally it's not taken into account in models. So this is reflection all the time. And here there is no reflection with the clear sky. Below.
What instrument do you use to measure the photometer aperture?
It's called LICO 6400. So it was a tree climber. So it was very funny. So you were going to say cut top sun. So the guy was cutting. You throw with a stone the leaf. You have 10 minutes because the leaf does not really realize that has been cut. So you are clipping this, and then you are really with a laser, you are really just under certain circumstances, under conditions of radiation and also concentration, you are measuring the stomatal aperture.
So it's a chamber measurement.
It's a chamber measurement.
Okay, so you clamp the leaf on a chamber, the exchange, and the change of concentration with time gives you the flux. And the flux, it has a relation with
and it is a very manual. The rest of the campaign, it was almost continuous, but this requires, it was 4 people, 2 tree climbers, 1 person collecting the leaf and the other clipping all the time, making the measurement. So we did it 3 or 4 days, and we have all this diurnal variability. But it's still a lot of scatter, because we were collecting leaves randomly from the trees. So here, this is why I ask a biologist would kill me probably, because we don't know which tree was.
Even different species.
These are different species. Yes.
And so Umberto asked another question. So he says GS reduces with VPD. I'm not sure what it is, but especially in the afternoon. Did you measure turbulent latent heat?
Yes.
at the tower?
Yes. So this we get all the data, and it's the water vapor deficit, and we are going to relate it to the water vapor deficit. But the model includes this, so the mechanistic model includes the water vapor deficit. So, and what the midday depression is represented by the model. Got the question?
How do you classify the clouds? You said shallow clouds, shallow deep. What approach is used to classify clouds?
Well, here we use the, and I think Luis knows more than me. Let's see what it is.
We have used the radar now.
Yes. So we are classifying at 5 different stages. So we are taking a criteria on stability, precipitation, and certain amounts. So, what we are noticing, at least we were using this paper from Alice Henkes, and then depending on the stability in the morning, depending also on the precipitation, depending also, we had some cameras there. So we had some continuous cameras that we could really see all the clouds and deep convection. So there we had 5 or 6 criteria to define. What we are seeing, and that's a bit surprising, is that there is, if you look to the cloud base and cloud top and the radio soundings, if you go to the radio soundings, there are very little changes. So it's the change, I would say, is very subtle. So we are still investigating what could be. But the changes right now from all the complete data is that there is very little, no matter we are doing this classification, also based on the visual camera, the changes between the thermodynamic state and the states of the surface of fluxes is very little. So surface fluxes, for instance, they hardly change. So it's very subtle, locally speaking, very subtle to know. So what we are now making some runs is that perhaps the shear is different, and that's a bit what Mikhail was also studying, and perhaps the moisture at the right level. But so far for these 10 days, we have not so much evidence of what was, no matter we are applying a different criteria, what was the difference producing shallow cumulus and shallow deep.
And the cloud-based, say it's...
The cloud-based is very similar if you look to here. This is the data from Campina, from Ruiz Group. This is the cloud base from the shallow deep. This is this, and it's very similar. Cloud base is similar. Cloud top is, of course, in the deep cases here. This is a typical thing that you see the cloud top. And the boundary layer, this is the boundary layer height, is very similar. So this is still work in progress. No matter we have these different criteria, it's very difficult to really see something, who is the main driver here.
We have seen in the logs of data that this is quite stable during both of the 2 years of sampling. There's a change between mods.
Okay.
But you saw 3 weeks only, so it's going to be really stable. It's a characteristic time for that period.
Yeah.
For example, in January or March, it will change, but there's a January of this high, a
Okay.
March of this high.
But so far for this data, we have this criteria, but difficult also to distinguish what is the main driver.
Okay, so any more questions? I have one. I just the last one maybe. It's about the 3x3x3 simulations. I was wondering because in this scale, you are approaching the DNS.
Yes. Well, no. I'm very far away of the DNS.
DNS is what? Centimeters?
No, it's molecular viscosity.
Ah, okay. I thought you were approaching already.
No, the DNS can do. DNS is you simulate DNS, but you simulate the DNS like then you solve molecular viscosity, but then the Reynolds number you cannot have the atmospheric Reynolds number. It's like you are simulating an atmosphere that is like with millets, with a lot of viscosity. So then you do DNS, but the Reynolds number is 10-4. So I'm quite far away of the DNS. The only thing is that I'm solving, if this is 36, I'm solving quite a lot of the main explicit simulation. So, but I'm quite far away of DNS, because DNS is molecular viscosity and not subgrid. Still here, I think we calculated, for the first point we had 100% subgrid, but after the second or third point, we can ensure that 70-80% of the eddies are explicitly solved. If not, you don't get this.
Yeah.
That sort of intrusion. Look to the intrusion that reaches, this is dry air that enters here until canopy, and this is all of a sudden a blob of moisture that moves from there. And I think for the chemist is extremely important. That would be my... And I don't think, if I can say something, this is not turbulence. It's like a mass flux. I would call it advective flux. It's not really, the way of organize the turbulence is not like typical eddies. It's more that all of a sudden you have a blob and flash. So it's more a mass flux emission and this. So it's not a very intermittent.
I would guess it also changes cloud formation, because you can have like bubbles of moisture on certain regions.
Yes.
And then the clouds will start growing from there, and then they start growing from there, and so they suppress other clouds. And this kind of thing.
Do we have 2 minutes? I can show you. It's a video that Jonathan Williams took. Let's see if I found it well. What he did is was also some years ago. I don't know why he did it. He did it a bit. It's a video of. I think he is releasing a smoke from atom.
Okay. This is the 25-meter one. Drugan has just lit the yellow smoke bomb, which will very shortly project 10 meters high yellow smoke, and we will see where it goes.
So that's quite funny. This is like a tracer. But you see that not everything goes up, eh? Now everything you think that goes up, all of a sudden it's broken in.
So it's really just going up. It's really ventilating rapidly out of the canopy. Some twists.
Some stay there handy.
The sun has gone very high.
And here,
It's split off into 3 groups now. It's now swirling back.
and then it goes down. And that's one, but the other is
Ah, it's
fascinating.
beautiful.
The other is fascinating because he emits from inside.
Excellent. Okay.
It's a blue tracer. It's
So we're just
now
firing
emitting
at
from
15, and it seems that most of the smoke has actually gone down, not up. So we're seeing none of it yet. Let's see if we see it come out of the canopy. Oh, yeah, there it is, coming up upstream.
Here. But it
That's
takes
weird.
20, 30 seconds. Here it is, eh?
The 15-meter one is staying in the canopy. Yeah, we can see it now! Staying in the canopy mostly.
It takes a while.
It's behind that tree. Let's see if it rises up. I can see it's locked in the canopy. The canopy is really locking it in.
It takes a lot. Time.
Yeah, now it's emerging.
It shows up in another place.
That's interesting. It's going in a completely different direction to the other one. That's interesting. So from 15 meters, the blue smoke heads out at a completely different angle, and seems to be keeping a much more collective plume. It's not
Compared to the yellow one, eh?
spreading so much, I would say.
Should be the color.
That's, now you got me with it could be the call.
What about the size of this smoke?
This I don't know. I think he did it by. It was very funny because I think he did. He had the idea. This is a colleague from MPI. He brought some that from, and then he said, "Well, look at this, Jordi," and I was fascinated. He is more a chemist, so I thought this is very good, and we cannot simulate this. This is very, but I think for the chemistry it's extremely important. And it's what you say also, how it's organized and moisture blobs.
But you asked about the size of the smoke, no? So it's the same volume of smoke.
No, the size of the
Ah,
fire.
so it's
Oh, this I don't know. I think
Probably the same.
I think it was the same thing. So I think it was some trace. I don't know. But I found this experiment. It should be repeated.
Yeah, I agree.
It should be repeated very systematically. I think.
more smoke.
Okay, so now we're moving to the author presentation.
We can take a small break maybe, otherwise,
Sure.
yeah,
We will take like a
change gears.
5-minute break, and then we will be back shortly.
So at one point I can send you the figures, and if you are interested, I can send you
with Oscar. And so if you know more about you than I do.
So my name is working in Jordi's group as a researcher teacher, and where Jordi gave an overview of everything that we did at Arto during our campaign Cloud Roots. I'm going to talk about one specific measurement technique, scintillometry. The instrument is called the scintillometer. And how it can help us to measure land atmosphere exchange processes in complex landscapes. And when we talk about complex landscapes, we think about maybe an urban setting or something where the surface itself is very complex. But the complexity here is very much, Jordi already pointed it out, by the clouds. It's complexity in two ways. It's for the area as a whole, it's very diverse. There's shades here and then not there. But if you are in a single location, the local conditions change very fast. And those are the two ingredients where, well, I already gave you my conclusions, but which we will reach. Wouldn't it be nice to have an observation technique that either averages all these fast changing patterns out into one integrated measurement, a scintillometer, or if we measure much more locally, that we can measure fast enough to measure the exchange processes happening at these very fast time scales. And that's something that we can do with scintillometers as well. Well, the motivation to talk about the scintillation technique is, well, I've been working with scintillation technique for a long time already, so I know a lot about it, but also we are starting a collaboration with Luis and Guido, working with scintillation data that we gathered during Cloud Roots, but we also left one scintillometer for the cafe campaign. So we had one scintillometer, and so here's a picture. It consists of a transmitter installed at Arto and a receiver installed at Instant. So it measures the sensible heat flux over a distance of 600 meters at a height of 60 meters. And it's a data set that started in August 2022 and it lasted until February 23. And I think Luis and Guido will be happy to see that there's data. That's all I want to show with this figure. So I will touch a number of things here. I will tell you a little bit about what scintillations are to begin with, and how we can use that phenomenon to build an instrument around this phenomenon. So that's, and then talk a little bit about the scintillation method. So it talks about 3 processing steps from the raw measurement to the fluxes of sensible heat and latent heat that we're interested in relation to the aperture diameter d. So that's the size of the instrument and the wavelength at which the instrument is operated. And so, yeah, you can see this as a sort of maybe a little bit of a lecture, and then we get to some scintillometer applications, and there will be some research as well. So first, what are scintillations? These are scintillations. Yeah. So where are we? We are in the Midwest, in the US. It's a dry wheat field, no water to be evaporated. A lot of sensible heat flux, and I think you've all seen this once, you know, over a hot road or whatever. You can see here with your naked eye turbulent eddies transporting heat. And what then happens is that the light that is from a distance on its way to the camera that is located here, is that it interacts with this turbulence. And it interacts in the, through refraction and diffraction. So the beam of light through the turbulent eddies that act as sort of lenses, they are changed direction and they focus and defocus, causing this dancing and in light intensity fluctuating effect. And that's the scintillation effect. And intuitively, you can already understand is that the stronger this effect, the more heat is being transported. Yeah, so that's in a nutshell. If you would have said you only have one slide, Oscar, I would have shown this one because it sort of explains everything. And then what is a scintillometer? Well, that's an instrument that measures the intensity of this effect. So it consists of a transmitter that sends out a beam of light at a certain wavelength with constant intensity. And then at a certain distance, you place a receiver, and there we measure intensity fluctuations because the light that's on its way from the transmitter to the receiver is going through an atmosphere where temperature and humidity is being exchanged with the surface, and those cause, well, rather I should, I didn't do this. So I'll follow the bullet points here. So there's heat and water vapor transport. Yeah, those are the plumes that we see here. Those cause temperature, humidity fluctuations in the air by individual eddies that are doing the mixing. And these change the density in that eddy is different than the surroundings. So we also have fluctuations in N, the refractive index. And that causes intensity fluctuations here registered at the instrument receiver, which we analyze as a variance, yeah, over a certain time. And then the scintillation technique, of course, travels the other way around. We measure this, we will relate it to N fluctuations, temperature, humidity fluctuations, and fluxes. And this distance can be, depending on the type of scintillometer, between 100 meters and 10 kilometers. Okay. A little bit of the physical principle behind it, it's diffraction. So where light is bent around obstacles as it forms new wavefronts at the obstacle edges. So here we have a point source, a scintillometer transmitter, and here we have a receiver over a path length L, and this is X that indicates the position along the path, and at position X we're going to place a turbulent eddy, an obstacle, of a certain size. And you see part of the eddy is also transparent, so light can go through. And now what we can do is we can sort of find the eddy size that is such that when it's bent here at the edges of the eddy, that the path length of the bent light is half a wavelength different than the light that travels straight through. And that causes a perfect scintillation because then the light cancels. And well, this is pure geometry, it's Pythagoras that we have to apply here. And for each position along the path, we can define what eddy size that is. And then that's not a completely maybe obvious argument, but the eddies that are in the middle are weighed most by this scintillometer. So for X is half the path length, we then arrive at an eddy size, the Fresnel length, F is lambda L, the square root thereof, that gives an order of magnitude of the eddy size that gives the maximum scintillation. Yeah? So this is an important length scale. And there are more length scales involved in describing the scintillation technique. Transmitter, receiver, a lot of eddies in there. And there are a lot of, well, there's some length scales that we can name related to the instrument, so scintillometer length scale, and some to the turbulence that is in between the transmitter and the receiver. So the path length L is important. The wavelength at which the instrument is operated is important. They all have units, meters. The Fresnel length we just introduced. The position along the path is important. And the aperture diameter. So not all eddy scintillometers are point sources, but they have a finite size, and then all the scintillation effect is averaged out over a lens or an antenna of a certain size. And that's another length scale that is important. And the height above the surface. And the closer we get to the surface, the stronger the scintillation effect. Turbulent length scales, well, it's just the size of the eddies, and most of the time we look at the inverse thereof. So we look at the 1 over the size of the eddy. We call that the eddy wave number, K. And from all those eddy sizes, we can define one that represents the largest eddy, the outer scale, and one that marks the smallest eddy that contributes to turbulent transport. That's the inner scale. All right, with those ingredients, let's now build a scintillometer. So now we're going to go to the method to do scintillation measurements and relate it to fluxes. And we're going to, along the way, also then define different types of scintillometers as a function of the aperture diameter and the wavelength over which it is operated. So it's not really an instrument, this scintillometer. It's a family of instruments. Yeah, so these are a number of optical scintillometers, very big aperture, smaller aperture. This is a laser scintillometer, so it's a point source. And this is a microwave scintillometer. It doesn't use light, visible light, or near-infrared, but millimeter waves. And what we will see, already jumping ahead a little bit, is that these optical scintillometers are mainly sensitive to temperature fluctuations, just like when we see scintillations, we see mainly dry air scintillations, and those are related to the sensible heat flux. And microwave scintillometers, they are more sensitive to the humidity fluctuations, and they become related to the evapotranspiration. The method in a nutshell. We have here a transmitter and a receiver defined by a certain aperture size and a wavelength. We measure the intensity fluctuations after the beam light travels through a path of turbulence. And then there's 3 steps to go from this raw measurement to the fluxes that we're interested in. So the sensible heat flux and the latent heat flux. And there's also a scintillometer type that allows us to resolve the mechanical turbulence. So this is a measure for the momentum flux. So I will go through these 3 steps, but just to mention them quickly. The first step relates the intensity fluctuations to a measure of fluctuations of the refractive index. And this is called the structure function parameter. Who has not heard ever of the structure function parameter? All of you have heard of the structure function parameter. No. Today. Oh, excellent. It's the expression is given here, and really what it is, it's a measure for turbulent intensity fluctuations in the refractive index. So what you recognize here, it takes the refractive index or time series of the refractive index in one location, that's R1, minus the refractive index fluctuation, a time series, turbulent time series of the refractive index in another location, and it takes the difference thereof. Takes the square root and then averages. If I would replace this by the average, you would recognize it's a variance, right? If we look at the time series and we take the difference with respect to its mean, take the square root and then the mean, we recognize this as a variance. And this is really a spatial way of looking at intensity fluctuations. And then that part is then scaled by the distance between the 2 measurements to the power 2/3. Again, see it as a spatial variance, to summarize it very shortly. Some scintillometers also solve the inner scale. Cn squared can be related to temperature and humidity fluctuations, also expressed as a structure parameter. And then we arrive, have you all heard of MOST? Mono-Obukhov similarity theory. It's what micrometeorologists use to link turbulence parameters to fluxes. Okay, I'm going to tell a little bit more about each step. So first step, it's a theoretical model that explains the intensity fluctuations. I'm going through this sentence. So it explains the scintillation strength, expressed as this the variance of the intensity fluctuations, as the integration of turbulence and wave propagation properties over all turbulence scales. That's this K, one of the length scales that we introduced, and the path, that's the X, between the transmitter and the receiver. Yeah, so this is a model without any introduction. This is what it is. And all the variables that you see here are the length scales that we just introduced, so that have either something to do with turbulence or have something to do with the instrument, except this, which is the spectrum, the turbulence spectrum of the refractive index, which is prescribed in this method. And this is a typical shape of the turbulence spectrum that is prescribed, where at large turbulent scales, so this is the spectral density, K is the eddy size, so it goes from, or the inverse of the eddy size, so here we have large eddies, here we have small eddies, that at relatively large eddy size, turbulent energy is being produced. And then between this outer scale and inner scale, we have the so-called inertial range, where eddies, due to the turbulent mixing, are chopped up into smaller and smaller eddies. So we go here from bigger to smaller eddies. But they don't, no energy is being added or removed from the pool of eddies that act at these eddy scales. And this is a Kolmogorov that found out this inertial range, and that it has a fixed slope if you plot it on a log-log scale, and then it's constant times Cn squared. There it is. The Cn squared defines the height of this spectrum, and the k to the power minus 11/3 defines the slope that we see here. So what we need to prescribe is the part of the turbulence spectrum that our scintillometer is sensitive to. Some scintillometers are sensitive to very small eddies. And here we get into a different region of the turbulence spectrum where the eddies get so small, where we get into the DNS of Jordi, which is not resolved by LES, and the turbulent eddies are dissipated. And so here the fluctuations in the refractive index quickly go to zero. And this part of the spectrum, there's a model by Reginald Hill that describe how the spectrum here goes to zero. And the transition between the inertial and the dissipation range is marked by this inner scale, which can be larger and smaller. And that's another turbulent parameter that needs to be resolved if we have scintillation measurements at this scale. So to recap, we have our theoretical model. We prescribe a spectrum, and depending on whether our scintillometer is sensitive to inertial range size eddies, we need to prescribe this spectrum model, which only depends on Cn squared. And if we're sensitive to very small eddy sizes, we need to have prescribe the Hill model, which depends on Cn squared and the inner scale. So we're sensitive to two turbulence parameters. And then you can show that, so that's if you read this in a paper, you must also always be careful, because then they make a huge leap. But you can show that scintillometers are sensitive to one eddy scale, which is the largest of the diameter of the optical element, or the Fresnel zone, whichever of the two is largest. And then if that eddy scale is in the inertial range, we prescribe the Kolmogorov spectrum, and it only depends on Cn squared. And if it's in the dissipation range, we are sensitive to both Cn squared and the inner scale. And then for long path applications, so say, if let's call long larger than 500 meters, we're only sensitive to the inertial range part of the spectrum. And then this double integral model has an analytical solution. So we can relate the variance of the log intensity, what we measure from the instrument, to Cn squared, the turbulence parameter that we want to solve. And it's related to the path length. So this is L to the power of 3. The longer the path, the more scintillations we see, the higher the variance. And the Fresnel zone to the power minus 7/3. And if we have a large aperture, so this is for microwave, it's always the Fresnel zone. Because the eddy, the lambda is so big that over 500 meters, the Fresnel zone is, say, larger than half a meter or a meter. So it's always bigger than D. For an optical scintillometer, where the wavelength is much smaller, typically the aperture diameter is way larger, and the F is here replaced by D. Okay, now it gets simpler. Cn squared to Ct squared and Cq squared. That's well, this relation where the Cn squared at a certain wavelength depends on Ct squared, Cq squared. So it means depends on temperature, humidity fluctuations, and a correlated term weighted by a wavelength dependent constant. And these constants are such that for optical wavelength, this first term is dominant, and the second and third term can be ignored or simply, or in a simple way, parameterized. And at millimeter wavelengths, the Cq squared is the largest one, but these two cannot be resolved or cannot be ignored, which is a problem because we have here one equation with three unknowns. So then typically what we do is we combine an optical and a microwave scintillometer. We measure the variances of the optical and the microwave and a correlation term. And then we can resolve three Cn squareds, one for the optical, one for the microwave, and one for the correlated term. And then we have three Cn squareds, three equations, and we can solve Ct squared, Cq squared, and Ctq. So when we, to put it short, with the optical, we can measure the heat flux, sensible heat flux. If we're interested in the evaporation flux over long distances with such a microwave scintillometer, we was resolved to this bichromatic method with two scintillometers. If we have a scintillometer that is sensitive to this inner scale, I didn't tell you how to resolve it. I will get to that when I get to the application. This inner scale has a direct relation with the dissipation rate of turbulence, which in turn has a link with the momentum flux. So that's an added bonus for scintillometers that are sensitive to the inner scale. And then last, two fluxes following Monod-Markov similarity theory. So you can write the sensible heat flux as the square root of Ct squared. The height is important, the rho Cp, so some constant of the air, and then an exchange coefficient, K, as a function of U star and a stability coefficient. And to calculate this exchange coefficient, for that we use Monod-Markov similarity theory. Yeah? But the most important thing to see here is that H and Ct squared and the evaporation and Cq squared are directly related to each other. So to recap, we've just been creating a cookbook on how to make scintillometers depending on the aperture size and the wavelength. It's the D or the Fresnel zone that depends whether scintillometer is sensitive to Cn squared alone or Cn squared in this inner scale. That was part one.
and the wavelength determines whether the scintillometer is sensitive to CT squared alone, so the temperature fluctuations, or CT squared and CQ squared. All right, with that, let's now go to some applications. So lecture is over, we're now going to look at some applications. And we're going to talk about long path scintillometers. So that's then the added value, remember how we started, of this type of scintillometer. So that's scintillometers that act over very long paths, and we integrate a lot of spatial variability over that long path. And that's then sort of special about this measurement, and they determine the fluxes typically also over a time scale of 10 to 30 minutes. We'll start with an optical scintillometer alone, with which we can determine the sensible heat flux, and then I show some results of an optical microwave combined system to determine the evapotranspiration. And then we go to these laser scintillometers, which act at a relatively short path, 100 meters or so. But there the special thing is that we can go to very short time scales to measure the fluxes, less than a minute. Okay. This is heterogeneity, not so much by clouds, but just by the landscape. So let's say that this is the area within your WRF grid, within one grid box. And in that one grid box you have green, you have brown, you have forest, and each surface patch has its own way of distributing the energy over sensible and latent heat flux. Wouldn't it be nice to have an integrated measurement that measures the average flux over this complex composite landscape? And so yes, so that we could do with a scintillometer. So we'll start simple with just a large aperture optical scintillometer. Transmitter, receiver, only measures the variance of the intensity fluctuations. From that we have 1 Cn squared. It's not sensitive to the inner scale because it has a D which is relatively big, 15 centimeters to 30 centimeters. It's optical, so it's only sensitive to temperature fluctuations, and these temperature fluctuations we can relate to a sensible heat flux. And what we did once, and this is already a while ago, in Lindenberg, Germany, so that's an observational site of the German Weather Service, in an area of about 20 by 20 kilometers, and each color here represents a different land use, especially a lot of different agricultural crops. We have here a scintillometer path over about 5 kilometers, seeing a mix of land uses. And what we did in this one campaign is place an eddy covariance system which measures in each individual field the flux. And they vary a lot. This is for one day. We see that the fluxes, depending on the land use, for the water, the fluxes are even negative, so there's heat being transported from the atmosphere towards the surface. We have the highest fluxes over the forest, a lot of heat going into the atmosphere there for the same reason. The forests don't like to lose their water, so they close the stomata and start to heat up the air more. And then depending on the agricultural crop, there's quite a variety of flux regimes. And then if we integrate all those fluxes to sort of a landscape scale flux, we get this line. And with the scintillometer, we have here the triangles, and we see that we nicely get the same flux regime. Yeah? This works if you are with the scintillometer relatively high, such that you are above what is then called the blending height, where the action of the individual fields is mixed into one soup, where the turbulence no longer recognizes it when it came from the one field or the other field. Another feature that is very important here is the footprint. So the area where all the eddies that contribute to the scintillation signal come from. from a typical flux measurement, that's this cigar shape, which is, it's a cigar shape, so it's long and elongated. And for the scintillometer, it sees a much, much larger area. Go to the combined method. Now we have an optical and a microwave scintillometer. We measure variance of the two wavelengths and a correlated one. We have 3 CN squareds from which we can determine CT squared and CQ squared, and now we also have as a bonus the evaporation. Remember that the microwave scintillometer alone, you cannot do much with it in terms of determining fluxes because it's sensitive to both temperature and humidity. You need the combination to distinguish the two. And here we did a quick experiment over the same area that we just looked at, and it overall works out more or less fine. We also, with time, went, we also did an experiment which is now ongoing at Cabal. Have you heard of Cabal? Louis knows of Cabal.
Yeah, the big tower.
Yeah, it's the big tower. It's, this is the Cabal Tower. It's a 200-meter tall tower in the Netherlands for, you know, atmospheric research, especially boundary layer research.
Not like Atto. It's very comfortable.
Yeah, yeah.
There's competition. But the elevator hardly ever works.
Atto also has an elevator, but does not work.
For instance.
Anyway, we have two optical microwave scintillometer paths at Cabal. One is over a long path, 10 kilometers, from this tall tower at 80 meters to another very tall television tower at 10 kilometer distance. But now I'm going to show you some results over a relatively short path. We have these very nice, very stable towers, 10 meters tall. And then we have a path of 800 meters over the Cabal terrain. And you see that's, you know, nice, well-defined Dutch shortcut grass. So here the surface is relatively simple, good spot to see how well this instrument works. And what we try to do here is to do an intercomparison against the standard eddy covariance flux technique, but also an LES. So the same LES that Jordi just talked about, micro-HH. No, this is micro-HH, that was Dales. But also with a 3 by 3 by 3 kilometer grid. This is the area. Here you see the scintillometer transmitter and receiver. Here you see the eddy covariance and sort of the areas that they see. And I'll just show you the end result, the fluxes for one day. This is the sensible heat flux, this is the latent heat flux. And I think the thing to note here is that in green we have the eddy covariance, in blue we have the actual scintillometer, and in red we have the virtual scintillometer in the LES. And what you see here is that with the eddy covariance, this is a typical thing that you see. The fluxes go up and down quite a bit, but there's hardly any clouds. So that's a lot of statistical uncertainty that you still often see on nice sunny days in the eddy covariance fluxes, which you don't see over the path averaged fluxes with the scintillometer or in the virtual scintillometer in the LES. So much more stable signal. And the same for the evapotranspiration. Here we see even larger statistical noise, if you can call it like that, in the eddy covariance fluxes. We also try to measure fluxes over a lake, a salt lake in the Atacama Desert. And we thought we had it sort of installed at one edge of the lake and another edge of the lake, thinking that this area between where we installed it and where the lake actually starts was so wet that it sort of acted as a lake. We were wrong. So really, here the flux regime is very different than in the water. We had some sort of internal boundary layer developing in our scintillometer path. In the end, we got a nice agreement between the eddy covariance fluxes and the scintillometer fluxes, but we had to adjust the Monobukov similarity functions. So we had to tweak the relation between the structure parameters and the flux to get it right, because we had a disturbed turbulence regime. And I see this as a weak point in the scintillometer method, that this link is empirical and it's not as strong as you would like it to be. We also have a scintillometer set up in Amsterdam. No results here, but this is also a nice application over a very heterogeneous surface to determine the flux regime here. Last, very quick, with this laser scintillometer, remember that the special thing there is that we can go to very short time scale fluxes. And here, this is a scintillometer that is sensitive to the inner scale. So if we only have one beam, we have a scintillometer that is sensitive to turbulence parameters, and we cannot solve that. So here, what we do is we have a laser with two beams that are very close to each other. And we measure the variance of the beams and a covariance term, and that's the independent scintillation statistic. And from the variance and the covariance together, we can solve the Cn squared in the inner scale. Remember that this inner scale had something to do with the turbulent kinetic, the dissipation rate of turbulent kinetic energy. And from that, we can solve the momentum flux, which is nice if we do measurement very close to the surface, where the momentum flux is an important contributor to the generation of turbulence. And well, the video that we saw of cloud roots, we've done that before, and what was our first cloud roots experiment was a pilot in Germany near Aachen. And the same thing, you know, you've got clouds passing over, creating this shadow pattern over the day, and wouldn't it be nice to, over short path, see how quickly the surface reacts to these changes in radiation? Is it immediate? Does it react at all? So here we have, from that movie, a period between 9 and 3 o'clock local time. This is SPAR, photosynthetic active radiation, in gray, showing huge fluctuations. And in light red, so that's this one, we see the eddy covariance method, which needs 10 to 30 minutes at least to solve the flux. And it's not at all capable to see these fast fluctuations. And with the scintillometer, here operated at 6 seconds, completely independent measurement. One is radiation, the other one is a turbulence measurement. It follows, that's the dark red, it follows the fluctuations in the radiation perfectly. So light on, turbulence on, light off, turbulence off. Reacts very fast. But if we look with a bit more detail, here we look already with a bit more detail, you see that when the lines go up, there's a little bit of light between them. And if we look at a correlation function, we see that typically we need a time shift of about 1 minute to align the two with each other. So there's light goes on, system needs a minute to get active, and then starts transporting fluxes. If we combine this scintillometer with an infrared gas analyzer, we can also determine fluxes of CO2 and water vapor. So what we do here is that with the infrared gas analyzer, we determine a structure parameter for water vapor and CO2 and relate it in a similar way to what we've seen before to a flux at very short time scales of a minute, where the exchange coefficient is now determined by the sensible heat flux and the momentum flux from the scintillometer. So it's a combination method. And that this also works very well. We're on very fast fluctuations in light, lead to fast fluctuations correlated with CO2 and water vapor flux. And we can do all kinds of plant physiology analysis on this as well. And one of the things that because we also brought that laser scintillometer to Atto, is what we want to do is combine it with water vapor and CO2 measurements that we did at Atto, but not with the simple IRGA alone, like this one. But the inlet is here. And the analysis boxes are here, where we measure very fast, like 1 Hertz, CO2 and water vapor isotopologues. And the different isotopes of CO2 and water vapor are associated with the source areas. So it's in principle what we hope to get out of this is that we can do the partitioning of the CO2 and water vapor fluxes, whether it's coming from the soil or from the plant, by looking at this combination technique. So that's it. What I want you to take home from this is that scintillometer is not an instrument, it's a family of instruments, and there's instruments that can get you fluxes over very large integrated spatial scales. Another one is that other types of scintillometer can yield you fluxes at very short temporal scales. That's it.
So, questions?
Do you install this microwave too, or
No.
just only the optical?
Yes.
And for Atto to instant tower to what's the name of the other tower?
Triangular.
Tower was the same optical, same wavelength? No.
Yeah, so between an instant is a larger scintillometer, so that, and over between instant and the triangular tower, that's a path of about 100 meters. There we have a laser scintillometer.
To make this data
Yes.
goes to surface flux, right? What you need to do?
There's a
You're going to provide
yes,
different
I will
levels.
provide. So when I know a lot about, also talk about that we have to take care of with the installation, but one thing that sort on a log scale is linear. In here, but at longer temporal scales, we often see that this goes up again. And that's because at much longer time scales, absorption can also influence the signal intensity. So we need to bandpass filter
to get rid of this. So that's something that needs to be done with the raw data. And yeah, I mean, here we worked with very stable towers. Sometimes we also see that we have funny peaks. There's tower movement, we need to get rid of those. So to make a long story short, we always do some sort of spectral cleaning of the raw intensity fluctuations before we calculate the variance out of it, which goes to Cn squared, which goes to Ct squared, which goes to the flux.
In the data that you use, which level?
No, for Guido, I will have the Ct squared, I think is the most useful parameter to work with. At 1 or 10 minute time scales or a couple of flavors. Yeah.
This one question, so because you are measuring the variance, basically, so there's no way of getting like the result in range. You can only get the integral measurement. You cannot get like range result, right? Or not?
Yes, you can.
Okay.
But we have to go back to the cookbook. And one way to do this is if you have, say, one detector, one transmitter, and a lot of detectors over a range. And then the correlation over different distances changes the path weighting. So you have, well, there are a number of ways to do this. Another thing that we can play with is that the transmitter is big, and at the receiver side we have a number of detectors. One is small, other one is bigger, and so on. So what these different flavors of detectors do is they change the path weighting between transmitter and receiver. So if the two are exactly the same as what we have in this installation, the path weighting is like this bell shape. I didn't mention that, but this in fact is a very nice property of the scintillometer, that very close to the transmitter and the receiver, where your surface often is a little bit disturbed, the contribution to the scintillation signal is almost zero. And by playing with detector distances and maybe aperture sizes, you change the shape of the weighting function.
Like equivalent to like the satellite wave functions, something?
Yes. And from that you can, make a retrieval algorithm and resolve fluxes over the path. I've worked with a group that they are solar astronomers, and for them, scintillations is their evil. They want to avoid it, and they want to know what is the scintillation intensity over the whole of the atmosphere at any given point. And so they have a scintillometer, I've worked with them, that use the sun as a source and have a range of detectors over a bar of 2 meters long. You get these different weighting functions over the path, and you can resolve a profile of Cn squared over the atmosphere.
Cool.
Yeah. So it can be done.
Because I was wondering, then like Jordi's simulations 3x3x3 that shows like the canopy and so on.
Yeah.
If you get like a range resolution, then you could like validate something like this. Interesting.
What's going on when you have fog?
Yeah, so there are a number of things that disturb this. When you have so here we have intensity fluctuations around a mean signal level. And the mean signal level depends on how hard you switch on crank up the transmitter and the sensitivity of the receiver. And typically we sort of make sure that these fluctuations are in a nice detectable range. But once you get fog, the mean level goes down, and the fluctuations down, they get into they get to the zero level, or they're absolutely zero, and then the instrument doesn't work anymore.
So the mean signal level is sort of the carrier for the scintillation signal. If that signal is gone, we don't measure scintillations anymore.
Oh, probably had no fog during cloudburst.
Yes. No, when we went up now,
Yes.
in the morning it was very foggy.
It's extremely heterogeneous also.
Yeah.
We have these fumarolas of moisture moving up in the morning. And it's that smoke of moisture moving, so it's very heterogeneous with some fog eyes and so on. It's very different.
Thanks a lot. Well, thanks the talkers today again. I guess out of curiosity, is it very expensive instrument?
Yeah, so the optical scintillometer I think is in the order of 30,000 euros, more or less what you pay for an eddy covariance system. The microwave is relatively expensive, so combined optical microwave scintillometer systems quickly 100,000 euros.
Can be good for that.
Yeah.
To have it permanently also for remote sensing. Yeah?
Yeah.
Because you are more on a remote sensing scale also. So.
It's also good for us because for each scintillometer that you buy, we get a little revenue. That's
You get it, I will get it.
Thanks a lot. Okay.